this lecture, we're going to compute the cycle index of the octahedral group. The octahedral group is just the group of symmetries of an octahedron, and it's regarded as a permutation group of the vertices of the octahedron. So how do we think of an octahedron firstly? So let E1 be the vector 1, 0, 0, E2 be the vector 0, 1, 0, E3 be the vector 0, 0, 1. So these are the coordinate vectors in R3. The octahedron O is defined to be the convex hull of these vectors and their negatives. So we'll regard this as the set U, and the octahedral group G will be defined to be the group of permutations of U, a permutation group of U, and it's going to be consist of those permutations which are symmetries, and I will use the word rotational symmetries of the octahedron O, which is a geometric figure. Just to give you an intuitive picture of the octahedron, I have constructed it here using GeoGebra, and you can see that it's a figure which has 6 vertices, it has 12 edges, and it has 8 faces. And it seems to have a lot of symmetry. As you rotate it around, you'll see that there are many positions where you can get very symmetric configurations. So this has vertices 6, edges 12, and faces 8. Now I say rotational symmetries here because we do not want to allow any reflections. Now all rigid motions of R3 are either are composed of translations, rotations, and reflections. Reflections are not physically allowed. Like you cannot turn into your mirror image in three-dimensional space. So we do not allow reflections here, we only allow rotational symmetries. So rotation, since this octahedron that we've constructed is centered at the origin, all its symmetries are going to be linear transformations. In particular, they're going to be rotations about some axis that passes through the origin. So we just need to figure out an axis and an angle, and we'll know what the rotation is. Now, this symmetry calculation is very interesting in the study of isomers of atoms which have valency 6. So you see this kind of behavior in atoms like cobalt, sulfur, and sometimes even iron. So what you have here is an atom which we'll call M, and we are going to have we have 6 sites where various ligands can be placed. So let me just make a copy of this. So for example, if I have 2 ligands, say L1 and L2, you could think of them as maybe chloride or NH3, whatever you like, but let's just focus on the math here. So say I have 3 L1s and 3 L2s, then there are various different ways I can arrange them. For example, I could put all the L1s here, all the L2s here, or I could put L1, L1, L2, L2, L1, L2. Now these two molecules, they have the same chemical composition in terms of formula. They are ML1 cubed. I guess we should write the, so in chemistry we always write the multiplicity as a subscript. So I'll call these L superscript 1, L superscript 2. So these are both isometric. These are both isomers, not isometric. These are both isomers, but they will have different chemical properties because no matter how you take the isomer on the left and try to rotate it, you will not be able to get the isomer on the right. So in order to understand the different possible isomers that you can get with different ligands, we just need to understand the colorings of the octahedral graph, which again you can just visualize as this graph uh, under the equivalence relation provided by this group of symmetries, which are the rotational symmetries of the octahedron. So what we need to do first is to list all the symmetries of the octahedron. One way to run through all the symmetries of the octahedron is to classify them by the kind of axis that they are rotations about. So we look for axes about which there is symmetry, and so I'll make a table here. So there's an axis of symmetry passing through each pair of mutually opposite, diametrically opposite vertices. So I'll call this an axis of type V. So here you see an axis through this point here and this point here at the opposite end. You can just you can do rotations about such an axis. And if you look at it from the top above this axis, you will see that you can rotate by multiples of 90 degrees. So axis of type V, we have rotations by angle plus or minus pi by 2 or angle pi. Plus pi is the same as minus pi. Okay, and plus pi by 2 minus pi by 2 means we have two such rotations, and here we just have one such rotation for each axis. But to get the total number of such rotations, we need to know how many axes are there. So number of axes, well, remember there are 6 vertices, so there are 3 such axes. Okay, and so the total number of such rotations is going to be, here you're going to have 6 rotations of this kind, and we're going to have 3 rotations of this kind. And now let's just consider the most important thing. What is the cycle type of this rotation when it acts on the vertices of the octahedron? So for this, let's go back to our model of the octahedron, and you see, if you take this figure, I'm looking at it from the top of this axis, and you rotate it by plus 90 degrees or minus 90 degrees, then the north pole and south pole of this rotation, those are fixed, but the other points form a cycle of size 4. So here the cycle type is 4, 1, 1. And when you rotate it by 180 degrees, then what happens is that again you have these north pole and south pole are fixed, but this point here will get rotated to the point that is diametrically opposite to it. So we'll get 2 cycles of size 2 and 2 cycles of size 1. Okay, now let's look at an axis that passes through the center of an edge. So if we look at it this way, then we should, if we want to get a view that is, perpendicular to the axis, oops, I seem to have deformed my thing, yeah, there we go. Then I should try to get a view that is, yeah, so here you go. Oops, so now I have managed to, well, let's stop it here. Okay, it's not, doesn't seem to want to stop, but you get the idea. So you get this figure, and it has it has only one symmetry, which is 180 degrees. So we have to rotate by pi. Uh, and there's only one non-trivial symmetry here. And what does it do? Well, it's going to this square face in the, not face, well, the square in the center of the octahedron, it's going to just flip it around. So you'll get two cycles, two cycles, and also interchange these two poles. So you'll get cycle type 222. So the number of axes here, of course, it's 6 because there are 12 edges. The total number of rotations is 6, and the cycle type is 222. And finally, we have reflections about axes passing through the center of a face. So these are my favorite. So here is a face, it's an equilateral triangle, and if you want to just rotate it, then what you will do is you will you can rotate it by angle of 120 degrees, plus or minus 120 degrees. So this is rotation by plus or minus 2 pi over 3, and you have two non-trivial rotations. The number of axes is 4 because there are 8 faces, and so totally there are 8 such rotations. And their cycle type, well, you'll have this triangle up in front, that will form a 3 cycle, and the triangle that is behind it with the opposite orientation, that will form another 3 cycle. And so there are 3 cycles in such a permutation. And we mustn't forget, every group has the identity element. So that, well, everything is an axis if you wish. It doesn't do anything. See, the angle is 0. There's just one element. Let's just leave this blank. So totally there's 1. And its cycle type is 1, 1, 1, 1. 1, 2, 3, 4, 5, 6. Or sometimes we just write 1 to the power 6. So let's see, totally we have 9 plus 6 is 15, plus 8 is 23, plus 1, 24 symmetries of the octahedron. And in fact, you can cross-check this in another way using the orbit stabilizer theorem. The number of symmetries of the octahedron that fix one of its vertices. So if I want to fix this vertex here, then what I would do is I can only rotate it about an axis passing through that vertex and the opposite. So there are totally 4 symmetries that fix the vertex A, but then it's not difficult to show that this action of this permutation group on the vertices of the octahedron is transitive. That means every vertex can be taken to every other vertex. So the orbit of each vertex is of size 6. So the order of the group of symmetries is 6 into 4, 24. Okay, I'll leave you to think about that. I won't write down the details here. But now we are ready to write down the cycle index for this group. So Z G of y1, y2, well, you only need to take up to y6. This is going to be 1 over 24 times. And now let's write down the terms corresponding to each of these. So here we have 6 y1 squared y4, right? So there are 2 1 cycles and 1 4 cycle. Then we have 3 y1 squared y2 squared. Then we have 6 y1 squared y2 cubed, I guess. That's 3 2 cycles, plus 8 y3 squared plus y1 to the power 6. That's the cycle index polynomial. And if we substitute yi to be pi t1. So you can color this thing with up to 6 colors. So I'll just take 6 variables here. So this would be t1 to the power I plus t2 power I plus t6 to the power I. Then we'll get the Polya polynomial pg of t1 t6. And you can compute this with a little bit of hard work or a computer. And I just did this before recording this lecture, and it looks something like this: 30 times x1 x2 no, sorry, I should say t1 t2 t3 t4 t5 t6 t1 to t6 plus 15 x1 squared x2 x3 x4 x5 should be t1 squared t2 t3 t4 t5 plus 8 t1 squared t2 squared t3 t4 plus 6 t1 squared t2 squared t3 squared plus 5 t1 cubed t2 t3 t4 plus 3 t1 cubed t2 squared t3 plus 2 t1 cubed t2 cubed plus 2 t1 to the power 4 t2 t3 plus 2 t1 to the power 4 t2 squared plus t1 to the power 5 t2 plus t1 to the power 6. And there'll be a lot more terms, whatever terms you need to make this symmetric. So I'll write it as plus symmetric terms. Right, the point is that this is a symmetric polynomial. So it's enough to mention just the coefficients of one monomial of each kind. And from this you can just read off the number of isomers with different valencies. So for example, if all the 6 ligands were different, then there would be 30 different isomers that you could construct. I mean, it's quite surprising that it's so large. At least to me, it seems like a large number, meaning that this group, well, it's a group of order 24 inside acting on 6 points, and the symmetric group of order 6 is quite large. It's of order 720. So 24 inside 720. It's a small compared to the total possible symmetries of the thing. Here, for example, we are looking at isomers where you have 2 ligands, each occurring 3 times, which means that we are looking at a coloring with 2 different colors. 3 vertices are colored with each color. And so we should look for the coefficient of t1 cubed, t2 cubed in this polynomial. And if you look for that, you see that it is actually just 2. And in fact, these are the only 2 isomers of this kind.